Thank you so much, Shani. Okay, and our next presenter is Florin-Vladimir Stancu, Tomer Weiss, and Rafael Kufner dos Anjos, going to be speaking to us about foveated animations for efficient crowd simulation.
Right. So, good morning, everyone. Nice to be here. Let me start with some very quick introductions first. Hi, I'm Florin-Vladimir Stancu. Please just call me Vladimir. I'm a master student at the University of Leeds and the main author for this work. The other two authors are Rafael Kufner, also from the University of Leeds, and our very own Tomer Weiss from the New Jersey Institute of Technology. I would like to begin by saying this started up as my own final year of bachelor's project, and I'm very happy to be here now presenting it to you. We'll be going to the motivation and background research, followed by the hypotheses, then the method and how we evaluate it, and then the results and discussion. So let us begin. Generally speaking, computing high-quality graphics takes tremendous amounts of computational power, be it rendering textures, casting shadows, simulating cloth movements, or simply computing the complex shading models. The costs add up exponentially. One way to combat these costs is the idea of foveated rendering, where everything within the user's fovea gets rendered at high quality, but everything in the periphery is instead rendered at lower resolutions. Existing work on this includes variable rate shading, which is what allows us to do lower resolution rendering in specific parts of the screen to begin with, followed by work by Stenger et al., which tries to make the fall off from the fovea to the periphery much more accurate to the human visual system. Then Thurston et al. Improving upon this a step further by adding luminance conditions into the equation. Now, vision science backs the idea of foveated rendering because, as you may already be aware, our human visual system's raw density gets lower and lower the further away we get from the fovea. One thing that should be clear, though, is that we don't actually see blur in our periphery, we see pooled. That's to say, the rods that we do have in the periphery all get tied up to single neurons, so the information gets aggregated. One way to say this is that actually we see statistically. We know what's in our periphery, but the details are being lost to us. This leads to a major factor called the crowding effect. If you look at the center here on the cross and you try to figure out which direction the duck on the left is looking at, you will be able to tell. If you try to do the same with the duck on the right in the middle, you will find yourself unable to do so. This is the crowding effect, where we can see and know what is in the periphery, but again, the details are being lost to us. There has also been recent work which tries to take advantage of this crowding effect and the pooling factor in general. This includes this metamer foveation, which attempts to do the fall-off, the blur in the background in such a way that the pooled information by our eyes is the same as it would have been from the ground truth. To our eyes, it's all the same. Back to our original problem, our application is more than just rendering, especially in the context of game engines. Particularly, animation updates can be very, very costly. An extreme case of this is crowds, where you have thousands upon thousands of low poly characters, all with bone transformations and mesh transformations, mesh deformations, and that adds up to be the majority cost of the rendering pipeline. There has been existing work to try and accelerate crowds. The first is the idea of 2D imposters to replace 3D agents. Level of detail based on the prominence of the agent on the screen, as well as GPU-accelerated animation updates done via instance management in the GPU. However, what you might have noticed about these things I just talked about is that none of it tries to make use of the vision research we just mentioned. So, what could we use? The first is the crowding effect we were just mentioning. The second is flicker. Work by Gracincic et al. Tells us two important things. The first is that our perception of flicker peaks in the near periphery. The second is that based on a number of conditions, including the flicker's position in our eyes, we sometimes achieve something called critical flicker fusion, CFF. What this does is that the flicker in our eyes no longer registers as being flicker, but as being static. Think of a blinking light, instead of being blinking, it's just on all the time. That's how it looks to us. The third thing we can use is the double drift effect. If you look on the dot to the left here, you might perceive the orb on the right as going diagonally left and right. However, if you look at the orb now, straight ahead, you will realize it's actually going up, up and down, straight up. The reason why it looks like it's going diagonal is because of the internal shifting motion, which also goes left and right. The fact that our eyes mistake these two different motions as being one is what we call the double drift effect. So what do we observe? We observe that, one, in our periphery, we don't see movement accurately due to the double drift effect. We don't see flicker well, or we outright ignore it due to the critical flicker fusion. And we don't perceive crowded objects well due to the crowding effect. This leads us to our hypotheses. The first initial hypothesis that we have is that we can simplify movement in the periphery to save on computation. What you see on screen here is one such example, where the left is what it looks like fully animated, and going to the right, we see how it looks more and more foveated. We simply reduce the animation rate. However, as we were just saying, our perception of flicker peaks in the near periphery. So if you try to foveate animations, that will make them look clunky and create flicker, which might be perceived by the eyes. So we have an alternative hypothesis. We believe we can omit movements altogether in the periphery and save on computation. As we're dealing with crowds of very small agents with naturally high crowding, we believe the lack of animations will go unnoticed. We also have two further hypotheses we're going to test. The first is that the more crowding there is in a scene, the less noticeable foveation is going to be. The second is that if you have organized movement from our crowd, the foveation is going to be more noticeable. So let us now go over the methods. We test both approaches from our alternative hypotheses. We try the full stop method, where we omit movements altogether, and we do the dynamic foveation method, where we simplify movements based on the agent's distance from the fovea. What you see on screen here is the full stop method, with the green agents being fully animated and everything outside of the area having their animations completely stopped. The area, the green area, is what we call the foveal area. The second method is a dynamic foveation, where again we have a foveal area with all the animations going in a green area. However, everything outside of it will have its animation rate calculated based on the equation on screen. The important thing to note from that equation is that it leads to a fall off like the one outlined on the right. Now, what you've seen here is our Unity prototype for this project. It should be noted that we simply do simple crowd simulations using the Unity's built-in nav mesh. And the scenes that I'm about to present to you in a second are derived from common crowd simulation scenarios. Very importantly is that our goal here is to evaluate perception, not to optimize implementation. Optimizing the implementation is going to be subject for further study. So let us now go over the scenes. The first that you've already seen is the Wonder Crowd, which is our unorganized movement scene and has agents going all over the place. The first of our organized movement scenes is Square Marathon, where they simply go around in a clockwise rotation. Similarly, parallel columns, except now we have two very distinct groups. Then we have intercepting crowds, where we have two groups repeatedly clashing into each other. And the intercept, where it's the same, except now the intersection is orthogonal. With these scenes, we go through two main studies. The first is what we call the flat screen test, which is our more structured test. And the second is a VR test, which is more unstructured. So, with the flat screen test, we try to go through our main hypotheses. First, to see whether the full stop or dynamic foveation method is better. Second, to see if more crowding leads to increased foveation tolerance. And third, to see whether structured movement leads to decreased foveation tolerance. The setup goes like this. We have a staircase test using all 5 scenes as per recorded videos. As they are videos, and because we're using a flat screen with no eye tracking capabilities, we have a red agent in each scene acting as the focus point for the participant. The participants were also observed while undergoing the test to ensure that the results are valid. Now, it should be noted that the foveation stages of the staircase test go like this. For full stop, we start from a very, very big foveal area, and we slowly shrink it as time goes on. For dynamic foveation, we have each stage increasing the foveation factor from the equation. What this leads to is a more aggressive fall-off. And these are the stages on screen. The staircase test, to be exact, proceeds like so. We start from no foveation, and every 10 seconds we go to the next stage. At any given point, the participant can press the spacebar button to indicate that they've seen foveation, and then ask to indicate where they've seen it. If the answer is valid, that is, there was foveation happening where they had clicked, then it counts as a valid response, and they go back 10 seconds to the previous stage. If they go again and detect foveation happening again at the exact same stage, it gets treated as a double confirmation, and the user goes on to the next scene. If, however, the input is invalid, say at the very first is invalid because there's no foveation happening in a place, then they get notified of this and they go back 10 seconds again to try again. The second, it doesn't matter. The second study is the VR test, where we had users go through a modified Wondercrowd scene, wearing a head-mounted display with eye tracking capabilities. This is more unstructured. Here, we're simply playing with the foveation values to see if how low we can get before they notice it. So let's go over the results. First and foremost, here are the results for full stop. The red line here signifies where we believe the foveation starts to go into the user's fovea, so where we expect them to actually start noticing it. And you will notice that Wondercrowd to the very far right performs significantly better than the other scenes, and this has been proven to be a statistical difference. There is no statistical difference with the T-intersection scene, however, and we'll get to that in the discussion stage. There's very similar results for dynamic foveation. Wondercrowd performs a great deal better than every other scene, and the same applies for the T-intersect scene. Finally, once again, we can see here about where the user started to see foveation. Once again, the red line signifies where the foveation area, where the fovea area begins. And we see that this is all quite close to the periphery, as we had hypothesized, quite close to the fovea area. And to give you a visual representation of how this looks, you will see here both methods about the means we discover this most effective foveation methods. And you will see that at any given point, did they stop again? Okay. There. At least half of the agents on the screen are stopped at any given point. That is, the ones which don't have any highlights. For the VR study results, we've compiled the mean results of what everything means. However, explaining what these values mean might be a bit complicated, so I'm instead just going to show you what they look like in practice. Once again, the video is not working, whatever. You will see here that usually the user has the head-mounted display tracks the user's view, and you will see 3 highlighted agents here. These are the ones that the user has animated and the ones they're looking at, and everything else is stopped. It's a very similar result for dynamic, which actually works, and you will see that the highlight shifts. Once again, it's only a couple of agents actually being animated at any given point, and the rest are stopped. If you had trouble seeing how that looks like before, here's images of each to make it more clear. Now, in terms of performance, we've been looking at how many animation updates per second are happening, and we see that full stop performs generally better in the first 2 stages than it does dynamic at the very highest foveation stage. So generally, we believe that if full stop gets away scot-free, then we should be using that because it leads to better performance. So let's discuss the results. As we were saying before, Wondercrowd performs generally better than all other scenes. So we believe this confirms our hypothesis that more crowding leads to more foveation tolerance. However, as I mentioned before, we found that Wondercrowd has no statistical difference with the T-intersect scene. And we believe this is because in this specific scenario that you see on the right, we have 2 very specific groups which very high crowding, which generates a similar effect as it would in Wondercrowd. Thus, why they perform similarly. Nevertheless, because now we have confirmed that crowding leads to better tolerance, we believe crowding itself can be used as a driver for foveation. That's to say, if we have no crowding in one specific area, there should be no foveation there. But if we have a lot of agents in one specific part, there should be much more foveation in that specific part. We've also found lower foveation tolerance for scenes with organized movement, that is, the other scenes other than Wondercrowd. So does that confirm our other hypothesis that organized movement leads to lower tolerance? Fortunately not. You see, we've had a lot of false positives in the very early stage of the staircase test. A lot of the times in the very first stage where there was no foveation happening at all. So why is that? Well, we believe that what was happening is that the small movements of the agents were falling under critical flicker fusion, CFF. That's to say, our users were looking in one corner of the eye, and the models in the other corner were falling under CFF and looking like they're static, even though they're moving, which gets mistaken for our very own foveation. Moving onwards, regarding the 2 methods, full stop presented higher tolerance overall than dynamic foveation for all our scenes. It should be noted, however, that in our Wondercrowd scene, dynamic foveation performs generally a lot better. Generally good as well, with some models going as low as 5 updates per second. So because of this, we believe the reason why full stop perform better is because of what we had hypothesized. The dynamic foveation causes flicker in the near periphery, and that gets picked up. But full stop doesn't suffer from this, because due to the lack of flicker, the lack of animations, they just keep going. Additionally, as we've seen, full stop has better performance overall. Therefore, we believe that between the two methods, full stop is the preferred option, despite what you might originally believe. Finally, we believe that screen space frequency can also be used as a driver for foveation. If you look at the scene here, for example, the warrior on the horse, they have a very shiny sword. If this person were to be foveated, even if the user is looking away from them, if the warrior were to swing the sword high while foveated, that will cause a lot of flicker, and therefore was very highly likely to be seen by the user. However, with very grouped up agents, as we were saying before, due to the crowding effect, we can still use foveation, and we can use it heavily. So in conclusion, we believe the full stop method is better than the dynamic foveation method because, 1, it is more tolerated by participants due to the absence of flicker. 2, in the best case scenario, it can lead up to 99.3% less animation update operations. And 3, because of the simple approach, it can be combined with other previous work to accelerate crowds, which is subject for further study. Additionally, we've confirmed crowding does indeed lead to increased foveation tolerance in the case of foveated animations, regardless of which method is used. And finally, the effectiveness of both methods have been confirmed during our VR test. That concludes my presentation. Thank you very much for listening.
So Vladimir, thank you so very much for a wonderful presentation. We have time for a couple of questions for Vladimir. Come on up.
Hey, I was wondering if there have been any ground truth tests for foveation in like the optics field that then you could tune your curve to see if maybe that could have been feel more natural for the dynamic method.
When you say optics fields, could you clarify a bit what you mean?
Like for people's actual eyes, do you have there been a study for the shape of the curve of foveation for them that you could then tune your curves to?
We had considered this. However, since we wanted to first verify whether foveation works as an idea, we've tried to keep this research relatively simple to see if the foveations work. That is something that we've been considering for this study as well. However, we've decided it's better subject for future study instead.
Gotcha. Thank you.
Wait, question over here. Thanks.
Hi, I have two. Something I might have missed earlier in the presentation was eye tracking involved in either the flat screen or the VR test for the moving foveation target, so that the fovea would be centered on where the eye was specifically looking.
Right. So the flat screen test didn't have any eye tracking due to the limitations of being a flat screen, and because we wanted to avoid any differences in the simulations, we had to use videos to ensure the same conditions for all participants. So there was no eye tracking there. However, the VR test, and if I go back a bit, I believe this is going to play. You will see here that the highlight does indeed move because that is eye tracked. The reason why we have the VR test is because we want to see whether eye tracking works in practice. And as far as we can tell, yes, it does. People only see about 3 to 4 agents being animated, and everything else is not noticed by them. Another question there?
I just had one more.
Yeah, go on.
What other principles of basic perception or even psychology would you want to explore in the future and apply to this foveation technique?
One other thing I've considered is, for example, for the organized movement scenes, is people starting to look in the direction of movement, so looking ahead of where the character they're tracking is going. So, for example, a bit of a predictive foveation was something we've also considered. And I believe that would be an interesting subject for future study. But so far, I think that would be it.
Thank you so much.
I was going to ask, like, you probably answered this, but what equipment did you use for, like, the eye tracking and the headset?
So that was, if we go here, the HTC 5 Pro Eye, which tracks eye movement at about 90 or 100 hertz. So it's very, very quick, as far as I can tell. Any other questions? Oh, wait, one more.
Yeah. So you say you're saving computational power by using the foveated rendering. What exactly does the animation update contribute to that? In this study, I think you still have to loop through all of the crowds to see if they are in the foveated area. So how does that compensate to the entire computational? Yeah.
You are right there. The implementation that we are doing here, as we were trying to test, again, perception, not to improve performance, not to optimize the performance, is indeed quite naive, and therefore I am indeed looking through every single one of the agents here. However, we believe that because of how simple the full stop implementation is, it could easily be combined with some other acceleration techniques or other optimization methods to try and go through those specific agents relatively quickly. So yes, you're right. This is quite a naive implementation. However, we believe a better implementation which does take advantage of the lack of animations updates would indeed lead to a high frames per second improvement.
Okay, thank you.
And we have a little bit of time for one more question. Okay. Please join me in thanking Vladimir for a wonderful talk.
Give me this laptop.